In this lecture, we will study retardation test, and we will study the basic theory behind the retardation test, and we'll check the procedure that has been done in the virtual laboratory edulib.in. We will see how it is different from the procedure that we conduct in our department. So starting with the basic concept or theory behind the retardation test. This particular test is conducted on only shunt motors or shunt generators, or as a general I can say it is conducted only on shunt DC machine. This experiment cannot be conducted on series machines, that is because the entire experimental setup is on no load. So we can't run the series motor under no load condition. So we cannot conduct retardation test on shunt motors. Now the purpose of retardation test is to find out the stray losses. Now how do we find out the stray losses here is, we normally run the machine slightly above the rated speed or its normal speed. Once it reaches its normal speed, we cut off the supply from the armature, and we'll see what is the total time taken for the speed or the voltage of that particular supply or voltage across the armature to reach certain point, and based on that time taken we will calculate the rotational losses. Now this rotational losses, it can include friction, windage and iron losses, or sometimes this stray losses that we calculate will only be friction and windage losses, eliminating iron losses. Now this is all dependent on whether, when you cut off the armature from the supply, whether the field is excited or even the field supply is cut off. So based on this criteria we define the stray losses. Now if the field is remaining excited, it means that we will be including iron losses in the stray losses. If the field is also cut off along with armature supply, then whatever losses we get after conducting retardation test will only be friction and windage loss. Now why it is so? Because once you cut off the supply, the armature will not suddenly come into a standstill position because of certain inertia present in the armature. Now because of this certain inertia present, the actual supply is cut off. Now there will be certain kinetic energy that is present in the armature. Now this particular kinetic energy is completely utilized in order to supply the friction, windage and iron losses and or iron losses. Now this armature, when it slows down, it will be in the moving condition, because of which there is certain kinetic energy present. Even though the supply is gone, there will be certain kinetic energy present in the armature until the motors attains zero speed. So until then there will be certain kinetic energy. Now this kinetic energy is mainly used to supply the friction, windage and iron loss. Now whether to include or not iron loss, it depends on the excitation of the field. If the field still remains excited, then the entire the entire kinetic energy is used up to overcome the friction, windage and the iron losses in the field winding. Iron losses in the armature winding. Okay, if the field excitation is cut off, if in case when you cut off the supply to the armature, if the field excitation is cut off, so then as a consequence there will be no flux. So once there is no flux, the concept of iron loss doesn't come into picture. So whatever kinetic energy is present in the armature, that will be utilized only to overcome the friction and windage losses. So that is the difference between including iron loss and excluding the iron loss. So if the field remains normally excited once you cut off the supply, then The stray losses will be the sum of friction loss, windage loss, and iron loss. If the field excitation is cut off once the armature supply is also cut off, then the stray losses will include only friction loss and windage loss. Now I've told you we normally remove the supply to the armature and we calculate the current that is current sorry, we normally calculate the time taken for the armature to or for the motor to reach certain speed, and based on that we calculate the kinetic energy. So next in the next slide we will see how the time taken is related to the rotational losses or the kinetic energy. Clear? So here, now first we will assume that n be the normal speed in rpm, then omega is the normal angular velocity in radian per second, which is equal to 2 pi n by 60. So the rotational losses will be given by rate of loss of kinetic energy of armature. So this energy is nothing but it is the rate of loss of this kinetic energy is nothing but the rotational losses. So once you differentiate, this is the equation for kinetic energy, half I omega square, where I is the moment of inertia. This is the equation for kinetic energy. So the rate of loss of kinetic energy you get when you differentiate this particular expression. So I omega d omega by dt is the resultant expression. So now this is the total rotational loss. So if you substitute omega value equal to 2 pi n by 60, this becomes the resultant rotational loss 0.011 in dn by dt. Now in order to calculate the rotational losses, the first thing that we must know is we must know the value of dn by dt and we must know the value of I. But it is very difficult to determine the value of moment of inertia. So we have certain method through which we can calculate this particular rotational losses without having to calculate the moment of inertia. So that we will see in the next slide. So here, before that, here is a small example of how we calculate the rotational losses when we know the change in speed. So suppose the normal speed of the DC machine is 1000 rpm. When the retardation test is performed, the time taken for the speed to fall from 1030 rpm to 970 rpm is 15 seconds with the field normally excited. If the moment of inertia of the armature is 75 kg, then so the rotational losses, we have this expression. So when you substitute the value of I and n, also change in speed. So change in speed is given by these two values. So dn value will be change in speed from 1030 to 970. So this is the change in speed, and then the time taken will be 15 seconds. So dt, if you consider t equal to 0 as the initial time, so the dt value will be 15 seconds. So when you substitute, we get the rotational losses as 3300 watts. Now in this particular example, we know the moment of inertia of the armature, so it was easier to calculate the rotational loss. But we may not, in practical situation, calculating moment of inertia is a very difficult task. So without having to calculate the moment of inertia, we can calculate the rotational losses. Now that is by a method called as eliminating moment of inertia. Okay, so here first we'll be eliminating the expression I, and then through the retardation test we can calculate the rotational loss. So first what we do here is, two times the particular test will be conducted. First one, we will speed up the armature, will reach the rated speed, and we will cut off the supply. Okay, and then it reaches certain value of voltage or speed. We note down dn value, dt value. Clear? The next part is the same test is conducted again. Now we will not simply cut off the supply, but we will make sure that whatever the kinetic energy is present, it is being loaded. We make the motor under loaded condition. In the first case, the motor will be under no load condition. In the second case, the motor will be under loaded condition, in such a way that when you cut off the supply will be cut off, but now the motor will be connected to certain resistive load. Now this particular resistive load has to be pure resistive load. So the motor will be connected to the resistive load. Now the total kinetic energy will be utilized in two ways. One way, it will be supplying the stray losses. In the second way, it will be giving certain amount of power to the electrical load. So now since you have included the electric load, the time taken for the motor to reach these or to slow down or to reach zero speed will be much lesser compared to first concept, because now this particular electric load or the pure resistive load will act as a brake, due to which the time taken for the motor to reach zero speed will be much less compared to the first scenario. So first we'll calculate the dn by dt without any electrical load. Now we'll calculate dn by dt2 with certain amount of load on the motor. Now this will be equal to w, that is the stray loss, plus w dash. W dash is nothing but the amount of power dissipated in the electrical load or pure resistive load. In first case, total kinetic energy will be equal to only stray losses. In the second case, the total kinetic energy will be equal to stray loss plus the amount dissipated in the pure resistive load. So once you divide these two expressions, I and N eliminates, and the resultant expression is given by this. So if you know the T1 value, T2 value, and also the amount of power dissipated in electric load, then we can calculate the stray losses. Now T1 and T2, it is nothing but time taken. T1 is time taken for electric motor to reach certain speed under unloaded condition, and T2 is time taken for the electric motor to reach the certain speed at loaded condition. So based on those two values, we can calculate the rotational loss. Now we will check how this particular experiment has been conducted in the virtual laboratory. So this is the setup for virtual laboratory retardation test on DC shunt motor. I'll not go in detail because we all know how this particular virtual laboratory works. So I'll straight away get into the experiment. So now there is the theory explained. I'll skip this part. The apparatus required: voltmeter, ammeter, rheostat, tachometer, and stopwatch is required here to calculate the time. Next one, this is the experimental setup. Now here I'll just explain this circuit diagram. Now here you have the electric motor. This is connected to the supply. Here you can see this is a two-way switch. This is DPDT, double pole double throw switch. On one side it is connected to the resistive load, that is 1 dash 2 dash. This is nothing but it is the resistive load. 1 and 2 terminal of this DPDT is connected to the supply through certain rheostat. Now this is nothing but the starting rheostat. Okay, and here you can see the field is connected to the supply directly. It is not connected through the motor. Now this particular setup may look like the motor is separately excited. Yes, because once you remove the cutoffs, once you remove the supply to the electric motor, the field will still remain excited. If your DPDT is connected to 1 and 2 terminal, particular motor is connected to the supply. I'll show it again. So this is the motor. If this particular DPDT is thrown on to 1-2 position, then particular motor is connected to supply, that is 220 volt DC supply. If this DPDT is thrown to 1 dash 2 dash terminal, then the electric motor is removed from the supply and it is under loaded condition. You remove the supply, you provide certain load to the electric DC motor. But in both the cases, whether the DPDT is in left position or right position, the field will always remain excited. So from this particular test, we can say that whatever losses we get, it will include windage losses, friction losses, as well as straight iron losses from this particular test, because the field will always remain excited no matter what is the position of this particular DP/dt. This should be DP/dt. It is not DP/ST switch. This has to be DP/dt. This is DP/ST switch because this is double pole, but single throw. You have only one position, but here you have two positions. 1 dash 2 dash and 1 2, there are two positions here, so this has to be DP/dt switch. Okay, make a correction while writing the record. This particular switch has to be DP/dt switch. Clear? And this is the electric load setup. Clear? Now I'll move on to the next slide. This is your field rheostat, which will be under cutout position, and this is your starting rheostat, which will be under cut-in position. So the procedure, I'll just explain the procedure. Keeping rheostat R1, that is field circuit rheostat, in the cutout position, and rheostat R2 in the cut-in position. The load rheostat, you keep it in a fixed position. We don't vary the load here. And DP/dt is in the 1 2 position, that is here the DP/dt will be towards this side, towards this side. It will be connected to 1 2 terminal. So DP/dt switch will be initially at the right side. Clear? Okay, and the supply switch will be closed. So we close the switch. Now motor is brought to the rated speed using cutout rheostat as well as the cut-in rheostats. So then we take the various reading of voltmeter. So before we cut off the supply, we'll take the reading of voltmeter and ammeter, and then now the DP/dt switch is opened. This particular DP/dt switch is open. We'll simply open it. We will not throw it to the left position. We'll keep it open. Okay, this will be in the open position now. Yeah. So once this is in the open position, now we'll note down the time taken by the motor to slow down by 5% of the rated speed is noted down, and the corresponding reading of the voltmeter is noted down. Now here there is a small difference between the way we do the conduction. So in our lab setup, what we do here is, the moment we open the DP/dt switch, we note down the time taken for the motor to reach certain value of voltmeter. Like the armature voltage is measured, we will measure the armature voltage. We wait, like if it is 220 volt initially, we'll wait until it reaches 210 volt. Okay, that much amount of time taken will be noted down. But here they are telling we slow down till by 5% of the rated speed. We don't go according to the speed, we go according to the voltmeter reading. We have a certain point. If the voltmeter reaches that particular point, we switch off the stopwatch. Okay, so if like initially before opening the DP/dt switch, if the supply voltage was 230 volt, and after opening the DP/dt switch, the voltmeter starts to decrease. Now the voltmeter value, the armature voltage value starts to decrease. Okay, and it reaches certain value called as 200 volt. Now that time taken for the voltmeter to reach from 230 to 200 volt, that particular time is taken in our experimental setup. Okay, and next that time is taken. Now again we will connect the entire circuit as it is. Okay, now again the DP/dt is we will switch off the supply. We'll keep the DP/dt to position 1 2, and then we will switch it off. We'll switch it on. So once we switch on, now the DP/dt switch is opened, and immediately it is thrown to position 1 dash 2 dash. That is, now we open the switch and we throw it to the left terminals. And now we will see the time taken for the speed to reach the 5% of the rated speed. Okay, and that time is taken as t2 seconds, and the corresponding reading of ammeter will be noted down. So coming to our lab setup, so initially I told you we will see the voltage from 230 to 200 voltage. In second case also we will see what is the time taken by the motor to reach from 230 to 200 volt. So those values are noted down, and corresponding ammeter readings are also taken. Okay, now we'll make after we have taken this T1 and T2 values, we'll bring all the rheostats to initial positions. We'll open the DPDT switch and as well as the supply switch. Now for this particular experiment, if you have to calculate the copper losses, we require RSH and RA value. So another experiment, sub experiment has been conducted to calculate the armature resistance, that is using voltage and current method. I'll just skip this part because we don't do that in our lab setup. We'll simply calculate the RA value. Actually the only aim here is to calculate the stray loss. We don't have to calculate the efficiency of the motor, so we don't require the armature resistance part. So I'll just skip this particular procedure. So as those who are everyone those who are writing the record, make sure that you don't write this particular part, determination of armature resistance, because we don't conduct that particular experiment. So next there are the certain precautions. I'll just skip this. Yeah, now here is the experimental setup. See, there are certain I can't say this entire virtual lab is 100% reliable, because there are certain mistakes here, because this particular setup is still under development. There is certain research going on in this part, so there are certain mistakes here you can observe. So if, like, not in this experiment, in Hopkinson experiment there are certain mistakes in the connection and all. So wherever there are certain such mistakes, I'll just point it out. Okay, so first we will switch on the supply. Now DP will switch off this. We'll take the tachometer. Now we'll start the, we'll change the rheostat. Yeah, see actually in this, what is the mistake here is, before switching on this particular DP ST, this should be in 1-2 position. Okay, and then we vary the rheostat and reach 1500 rpm, and then we start the timer. Sorry, then we throw this particular DPDT position to 1 dash 2 dash, and then we start the timer, and we will check the time until it reaches certain value, that is 5% of the speed. That has to be the procedure here, but that procedure has been that procedure has not been shown correctly here. So make a note of this. The first thing, we will keep the DPDT at 1-2 position. We will close this switch, and then we will vary the rheostat till the tachometer reaches 1500. Once it reaches 1500, we will open this DPDT switch. We will switch on the timer, and till it reaches certain value, that is 1057. Here they have taken 1057. We'll note down that particular time. So then we'll also calculate the we'll also note down the corresponding ammeter readings. So this particular reading will show you 0 because the load is not connected. So we have to calculate only this voltmeter and this voltmeter value. Yeah. So yeah. Yeah, this is the observation they have done. This is without any load. They take 4 set of, in our lab setup we only take 1 set of reading, but here they have taken 4 set of reading, and time taken will be average of those values. So here you can see the speed range is not same, it is different. So they have taken average of those values, and similarly this is with load. So this is the voltage across the load, and this is the current across the load, and we take the average of those values, and the time taken, we have taken the average of those values. Okay, so this is the basic calculation they have done. Hence, the retardation test is conducted on the DC shunt machine and the stray losses are determined. This is not the inference that you have to write. Change the inference according to the way we have told in the lab. So these are the Viva questions. Now what I want you all to do here is, there are few batches, those who have already conducted the retardation test. They have readings. So use those readings to do the calculation part. Okay, because here whatever, I can't rely on these values, because the way the particular experiment has been done here is not exactly the way it has to be done. So these values, we can't rely on, these values are not reliable. So I just want everyone, those who have done, those batches who have done this retardation test, share your values with those batches who have not done. So everyone who is writing the record, use the calculation as well as observation that was that is observed in our lab setup. Okay, and then do the calculation part. Clear? So that's it. And change the inference. I don't want I mean, inference is, this is not the way of writing inference. So change the inference here. Calculate the stray loss and write the result and inference. Okay, and by next Wednesday submit the record. Most of the students have not submitted the record. See, if you don't submit the record now, then once you get back to college after this lockdown, once the college resumes, you need to write the entire record. You have to complete the entire record. So then it will be a very tedious job for you all. So before, on that note, I'm telling everyone to write the record now. So if it is possible, please try to write the record now itself, so that once you get back to the college, once the college resumes, you can only focus on experimental conduction and other aspects of the semester. You don't have to keep on writing the record. So that is the reason why we are telling this. So yeah, that's it. Thank you.